Friction. How to diagram forces for objects on level ground where a force is applied at an angle. As you may recall from the previous video, there are three categories of problems which we will be solving involving friction. Objects sliding or resting on a level ground where the applied force is parallel to the surface. Or objects on level ground where the applied force is at an angle, or objects on an inclined plane. This video focuses on objects on level ground where the applied force is at some angle. An example of a case like this would be a suitcase being dragged by means of a handle at some angle. This suitcase has no wheels, so it is literally being dragged across the surface, perhaps carpet. How would we diagram the forces on this suitcase? Well, the suitcase is moving across level ground. So first we'll indicate the level ground. Next, we need a suitcase. I'll indicate the suitcase as if it's being dragged on one side because it's being pulled by means of a handle, which makes a certain angle with the horizontal. So here is our suitcase. We know that the suitcase must have mass. Therefore, the suitcase has weight. So I'll draw a down arrow because weight always acts in the downward direction. And I'm placing that force vector on the object's center of mass. I'll label it as Fw for the force of weight. We know that this suitcase is being dragged by means of a handle, and that the handle makes a particular angle theta with the horizontal. So imagine that this is the force acting along the handle. I'll label this force Fa for applied force, because that force which is dragging the suitcase along really is being applied along the direction of the handle. We know that this force can be divided into two component vectors. Any vector, of course, can be split up into components. So there must be a horizontal component of the force, which is acting parallel to the surface. This is the force that's actually moving the suitcase along. Also, there must be a vertical force perpendicular to my other component. So I've decided to label these forces as force horizontal, or FH, and force vertical, FV. And remember, if the suitcase is moving to the right in this diagram, it's the horizontal force which is actually causing the motion in that direction. What other forces might be acting on the suitcase? If there's a downward force of the suitcase acting on the floor, then there must also be an equal and opposite force of the floor acting on the suitcase. We call this force the normal force. Normal means perpendicular, and this force is perpendicular to the surface. We know that these two vectors must be equal and opposite because, according to Newton's second law, if an object is at rest, or if it's moving at a constant velocity, then all the forces acting on it must be balanced. The suitcase is not accelerating up into the sky, and it's not accelerating down toward the center of the earth. So therefore, in the vertical plane, the suitcase is not moving. So Fn must equal weight. Finally, if there is any frictional force acting on the suitcase, friction always opposes the motion of an object, and so it would point in a direction opposite to the motion. The suitcase is moving to the right with a constant speed. Let me indicate that. And as it's moving at a constant speed, this means that the frictional force must be equal and opposite to the horizontal force. All forces must be balanced according to Newton's second law. I'll label this force Ff for the force of friction. In this situation, the presence of a vertical force means that the normal force will be different than it would if the object were simply sitting on the ground. For objects at rest, the normal force is usually equal to the weight of the object. In this example, by exerting a force along the handle of the suitcase, part of that force is split into a vertical component that you might call lift. It actually lifts the suitcase a little bit off the ground as it drags it along to the right. So therefore the normal force will actually be slightly less than it would be if the object were stationary. So I'm going to decrease the size of this vector accordingly. You might be wondering, how could we calculate what the normal force is in a situation like this? Well, the vertical vector and the normal force and weight are all acting in the same plane. They're acting in the vertical direction. Vectors acting in opposite directions combine by subtraction. So another way of thinking of this would be that whatever our normal force is, it's the difference between the weight of the object and that vertical lift, Fv. We could also say that since we have two upward pointing vectors, Fn and Fv, that their sum must equal Fw. So let me write a mathematical expression based on vector addition here. Fw, which is downward, equals the force of the floor acting up on the suitcase, which is the normal force, plus the vertical lift on the handle. So if we wanted to know what F of n, the normal force, is equal to, it's simply the difference between weight and Fv. If this suitcase were being pushed instead, then Fv would point downward, making the suitcase seem heavier. The vertical force would then add to the weight of the object, and the normal force would be larger than usual. So when a downward push is involved, the situation is changed. If it were being pushed instead of pulled, then the normal force would be the sum of weight plus the vertical push. By pushing on the handle, it actually shoves the object onto the floor with a greater force than its weight alone would provide. So pushing along the handle would reverse the direction of this vertical force, and it would turn it into a downward force instead of an upward. The value of FH and FV can be calculated. As long as the magnitude of the applied force is known, and we know the angle at which that force is acting, then the cosine function would allow you to calculate the horizontal force, and the sine function would allow you to calculate the vertical force. In problems such as these, it is often necessary to know both values in order to solve the problem. So once again, if we multiplied the hypotenuse, which is FA, times the cosine of the angle, you could find the value of the horizontal force. And if we multiply the magnitude of the hypotenuse, FA, times the sine of angle theta, then it would allow you to calculate the vertical force. Remember that if coefficient of friction is involved, the coefficient of friction is calculated as FF divided by Fn, that when the force is applied at an angle, it influences the value of Fn. And this must be taken into consideration when working friction problems. For objects being pushed or pulled by a rope or a chain, or perhaps being pushed by a handle at some angle to the horizontal. This concludes the video for objects where the applied force is at an angle.